dear students. Today we will discuss about heat. Okay. Now see, you already know that heat is a form of invisible energy which causes the sensation of hotness or coldness of a body. Okay. So, which causes the sensation of hotness or coldness of a body. Sensation of hotness or coldness of a body means whenever if you touch any body, we feel that is hot or cold there. When we can say that is a hot body is, let us suppose here we are taking two bodies A and B. If two bodies are in contact, if A is in contact with B, then if there is a transfer of heat takes place from B to A, if there is a transfer of heat takes place from B to A, then we can say B is the hot body and A is the cold body here. Okay? Or for suppose if you are taking A and B, if heat energy transfer from A to B, then A is going to be hot body, B is going to be cold body. So, which means whenever if you touch any of the body, after touching the body, if you feel there is a loss of heat energy from your body to that body, then we can say here we are the hot body and that is going to be the cold body, which means we feel cold. For suppose on touching the body, if you feel there is a receiving of heat energy or absorbing the heat energy from the object, or there is a transfer of heat from the object to our body, then we can say that is going to be hot body, that is. Okay. So, heat always transfer from hot body to cold body here. So, for example, if you are taking two bodies, let us suppose body A which is a hot body and body B which is a cold body we are taking. And whenever if both the bodies are in contact, if there is a contact is present, then heat flows from body A to body B. Heat is flowing from body A to body B, that is. After some time, gradually what happens there is, after some time this flow of heat energy from A to B stops. Okay? So, which means that here at this particular position there is called that as thermal equilibrium. Okay? The point where the transfer of heat stops or where there is a no transfer of heat takes place, that position we call that as thermal equilibrium. Thermal equilibrium. Okay. So, thermal equilibrium means no transfer of heat, no transfer of heat. Okay. So, during the case of this thermal equilibrium, where there is no further transfer of heat from one body to another body, in that case there is one physical quantity which remains same in both the bodies A and B. That body on that only we call that as temperature. That only we call that as temperature. So, means temperature is a physical quantity which remains constant in both the bodies which are in thermal equilibrium. That physical quantity only we call that as temperature. So, means heat energy and temperature both are completely different, because heat is a cause where temperature is a result. Due to the transfer of heat energy takes place between one body to another body, there is a change in the temperature occurs. So, that is why heat is a form, temperature is the effect here. Heat is the cause and temperature is the effect here. Okay. Then if you see the units, heat energy actually its units in CGS, it is of calories, and SI system that is of joules. Okay. And we already know that 1 calorie is equal to 4.186 joules, or approximately we are taking that as 4.2 joules. This is for 1 calorie, that is. If it comes to the case of temperature, temperature CGS unit is, we are taking that as degrees Celsius, whereas SI system we are taking that as Kelvin, that is. Okay? It is taken as Kelvin. CGS is degree Celsius, SI system is Kelvin. Okay? Because heat is a form of energy where temperature is the result because of due to heat energy. So that's why heat and temperature both are completely different. Okay? So during the time of thermal equilibrium, where the transfer of heat stops, where there is no transfer of heat there, then in that case the temperature of the body, the temperature in both the bodies or remains same. Okay? So during the case of thermal equilibrium, when two bodies are in thermal equilibrium, the temperature of the body is the same in both the bodies. Okay? So that is about thermal equilibrium, that is. Okay? Now, when we can say body is a hot body is when it is having higher temperature, if the temperature is high. And when we can say the body is a cold body is if it is having less in temperature or lower temperature, that is. Higher temperature one we call that as hot body, lower temperature one we call that as cold body. So whenever if you connect this hot body and cold body, hot and cold, whenever both are in contact, heat transfer from hot body to cold body, which means from high temperature body to low temperature body, that is. Okay? Heat transfer from high temperature body to low temperature body, that is. Okay? Which means the temperature of the body decides the direction of flow of heat. Okay? Which one? Temperature. The temperature decides the direction of flow of heat. The direction of flow of heat. Okay? So this temperature decides the direction of flow of heat means going from A to B or B to A. All that is depending on the temperature we are taking. As these temperature we are using degree Celsius and Kelvin, we are having a relation between the temperature scales is there. Okay? So relation between the temperature scales. Relation between the temperature scales. Okay? So we are having mainly three are there: Celsius, Fahrenheit and Kelvin. Total 3 we have. Okay? So of the three we are having the lower fixed point and upper fixed point is there, which means the minimum point and the maximum point, upper fixed point. This lower fixed point we are taking that as the melting point of ice. Okay? That is taken as melting point of ice. Whereas upper fixed point we are taking that as boiling point of water. Okay? So lower fixed point is melting point and upper fixed point is boiling point, that is. Okay? Then if it comes to the case of degree Celsius, this melting point is of 0 degrees Celsius and boiling point on Celsius scale is 100 degrees, that is. And if it comes to case of Fahrenheit, Fahrenheit its lower fixed point is 32, whereas upper fixed point it is of 212 degree Fahrenheit, that is. When come to the case of Kelvin, Kelvin scale we are having 273 Kelvin is the lower fixed and upper fixed is 373 Kelvin, that is. Okay? Now if you see here, as it is ranging from 0 to 100, so the range of this Celsius scale is we are having total 0 to 100 divisions are present here. Okay? So means on that thermometer scale, which is a Celsius scale, if you are taking the number of markings, the number of lines it is present is 100 we have. Okay? So 100 equal number of divisions. Okay? Now when come to the case of Fahrenheit, it is ranging from 32 to 212, that is. So its lower is 32 and upper it is of 212. Then 212 minus 32, that is we are having total 180 divisions we have. Okay, total 180. Whereas in case of Kelvin again, its lower fixed is 273 and upper fixed is 373. So that the range here it is about 373 minus 273 means again we are having 100 divisions are there for the case of Kelvin. If you observe here, for the case of Celsius, we are having 100 divisions. For the case of Kelvin, also we are having 100 divisions, that is. So, which means when there is a change of temperature by 1 degree Celsius on the Kelvin scale also, the change in the temperature is 1 Kelvin it becomes. Okay. So, very important one, when you are taking, if there is a change in temperature per degree Celsius, change delta T, delta means change and T means temperature. So, if you are taking delta T is equal to 1 degree Celsius, then it is also equal to 1 Kelvin. 1 degree Celsius equal to 1 Kelvin, because we have 100 divisions of Celsius is equal to 100 divisions of Kelvin, that is. Then we are getting 1 division of degree Celsius becomes 1 division of Kelvin, that is. Okay. So, that is why here I wrote the change in temperature, if it is 1 degree Celsius change, then on Kelvin scale that also changes by 1 Kelvin, that is. Okay. For example, if you are taking the relation between them, so that say for example, on Kelvin scale, if there is an increase by 2 Kelvins there, 2 Kelvin change is there, then it is equal to, on Celsius also we are having the same change, 2 degrees Celsius change you will get, that is its meaning. But when come to the case of this Fahrenheit, the number of divisions are more here, which is about 180 is present. As the number of divisions are 180 is present, that is why here it is not like Celsius and Kelvin in this case. So, when come to the case of this Fahrenheit scale, then we are having 100 Celsius divisions is equal to here 180 Fahrenheit divisions, that is. So, that here you will get 1 Celsius division is equal to 18 by 10 Fahrenheit divisions, that is, which is of 1.8 degree Fahrenheit. Okay. 1 degree Celsius division is equal to 1.8 degree Fahrenheit, that is, which means that if I raise the temperature by 1 degree Celsius on Fahrenheit scale, that is changing by 1.8 degree Fahrenheit, that is. Okay. For example, like this you can take, as 0 degree Celsius is equal to 32 degree Fahrenheit, then 1 degree Celsius becomes, raising by 1 is equal to, here if change in temperature is 1 degree Celsius, on Fahrenheit scale the increment is 1.8 degree Fahrenheit, that is, which means 32 plus 1.8, 32 plus 1.8, it becomes 33.8 degree Fahrenheit, that is. Okay. So, this is the difference we are having in case of degree Celsius and Fahrenheit relation, that is. Okay. Then this is the relation to the number of divisions of one scale to another scale, that is. Now, if you see the relation between the scales on temperature reading, for the case of temperature reading, then we have the relation C by 100, which is C means the Celsius scale reading we are taking and 100 means the number of divisions it has, is equal to Fahrenheit F minus 32 by 180, where 180 is the number of divisions for the Fahrenheit scale, is equal to K minus 273 by 100, again where 100 is the number of divisions for the case of Kelvin scale. If you are taking for the case of Celsius and Fahrenheit, then C by 100 is equal to F minus 32 by 180, that is. Okay. Then finally we got 1s, 9s, then C by 5 is equal to F minus 32 by 9. Okay. This is the relation to Celsius and Fahrenheit case. Then C by 5 is equal to F minus 32 by 9, that is. Then if it comes to the case of Kelvin, which is of K minus 273 by 100 is there, even for this also 0 getting cancelled and here we are having 5, then it becomes finally K minus 273 by 5, that is. This is the relation. So C by 5 is equal to F minus 32 by 9 is equal to K minus 273 by 5. This is the temperature scale readings between the three different scales, Celsius, Fahrenheit and Kelvin. This is the relation. Then how to do the numericals by using this relation is, for example, if the given temperature of the body is in Celsius is given, let us say for example like this. Given one is, let us say 20 degrees Celsius is given. I want to convert that into Fahrenheit there, like this. Then between C and F, the relation is C by 5 is equal to F minus 32 by 9, which is C by 5 is equal to F minus 32 by 9, that is. Okay. Whereas C is equal to, which is of 20 degrees is already given, by 5 is equal to F minus 32 by 9, that is. Then 5 ones and 5 fourths and 9 fourths, that is of 36 is equal to F minus 32, that is. Then F is equal to 36 plus 32, that is, which is of 68 degree Fahrenheit. This is F value, like this. Okay. So which means here 20 degrees Celsius is equal to 68 degree Fahrenheit. So if you are raising the temperature by 20 degrees Celsius, then its meaning is on Fahrenheit scale, the raise of temperature it is about 68 Fahrenheit we have, like this. And in the same way, if you are taking for the case of Kelvin, if you want to find the same problem, if you are using the case of Kelvin as 20 degrees Celsius, here we need to convert that into Kelvin, that is. This is for Kelvin if you are finding. When come to the case of Kelvin, C and K. So C by 5 is equal to K minus 273 by 5, that is. C by 5 is equal to K minus 273 by 5, that is. That 5 get cancelled. Then C is equal to, already given, is equal to K minus 273, where C is 20 given is equal to K minus 273, that is. Then from this we can write K is equal to minus 273 coming this side becomes plus, then K is equal to 293 Kelvin. Okay, this is the answer. So Kelvin K is equal to 293 K, that is. If you observe here, actually the temperature raised is of 20 degrees Celsius, that is. Okay. To that 20 degrees Celsius rise, 273 minus 293 minus 273, that also increased by 20 Kelvin, that is. Okay. So that's why for the case of Celsius scale and Kelvin scale, how much is the raise we have for 20, how much is the raise we have for Celsius? The same raise only we are having even for the case of Kelvin also. Okay. So this is the relation between the temperature scales, Celsius, Fahrenheit and in case of Kelvin, that is. Now as we already seen the relation between the temperature scales, now we will see what is the reason how these temperature changes causes in any of the body here. Actually here the temperature is mainly because of due to the kinetic energy of the molecules present inside the substance here. Okay. Whenever if you are considering any of the substance, inside that we are having the particles are present. These particles are moving in a different directions randomly in a different direction. In zigzag motion they are moving there. So that whenever they are moving in a different directions, one particle and another particle both are colliding there and finally there is a change in the temperature occurs there. Okay. See here. So actually here the temperature or the absolute temperature, actually it is directly proportional to the average kinetic energy, that is. Average kinetic energy, that is. Okay. So whenever these particles are moving in different directions, depending on the kinetic energy we are having, temperature is present. So means if you are taking the case of the temperature is more, which is for high temperature bodies or hot bodies, then the kinetic energy for the particles is more, which means that the velocity they are moving in different directions is more and more chance of more number of collisions here. Whereas if you are considering about a cold body here, the temperature of the body is less, which means that the kinetic energy for the molecules is less. Means the velocity in the random motion actually it is slow when compared to the for the hot body here when compared to the hot body, that is. So that's why whenever if you are connecting a hot body to a cold body here, if both are in contact, hot body means high temperature, that is, and cold body means low temperature, that is. If hot body is a high temperature, then the kinetic energy is more for them, whereas in case of low temperature, that is of here it is less. High temperature it is having more kinetic energy, and in low temperature the kinetic energy is less. As here the kinetic energy is more, means the velocity is more, whereas kinetic energy less means the velocity is less. Now we are taking the hot body is in contact with the cold body, which means the fast moving particles are now colliding with the slow moving particles here. Then during this collision, what happens there is, this fast moving particles, they are transferring their energy to the slow moving particles here, so that there is an increase in the kinetic energy of these particles for the cold body. As the kinetic energy is increasing, there is a rise in the temperature for low temperature body, which is for cold body. As these particles are giving their heat energy to the low temperature, that's why there is a decrease in the kinetic energy is present for hot body. As there is a decrease in the kinetic energy for hot body, means slowly the temperature of the body decreases. Here the temperature of the body increases. So the increase and decrease in both cases at one particular stage, both are coming to the same stage. That only we call that as the thermal equilibrium, where both the temperatures are same. During the time of thermal equilibrium, where the temperature is the same, we cannot transfer the heat energy from one body to another body, because both are having the thermal equilibrium, means both are having the same temperature. As the temperature decides the transfer of heat here, in which direction to transfer the heat. As both are having same temperature, we cannot decide whether it is a hot body or cold body. So that's why here, as the kinetic energy for them is both are same, means in case of thermal equilibrium, there are no further increase or decrease in the kinetic energies is present. Okay, so that we call that as a thermal equilibrium state. So the temperature of the body is directly proportional to average kinetic energy, that is. Okay, so as we know that all the bodies are not having the same temperature, depending on the kinetic energy present, the average kinetic energy present inside that one. Now depending on that, we are having different temperature is present there. Okay, and even though if you are supplying the heat energy to a substance here, all the substances are not increasing their temperature same, because whenever if you supply the heat energy to any of the substance, it doesn't mean that is utilizing its energy only for kinetic energy. Okay, some of them, they are using their energy for average kinetic energy. Whatever the heat you are supplying, heat energy Q, whatever the heat energy you are supplying, they may utilize it for average kinetic energy, they may utilize it for rotational kinetic energy, or they may use for vibrational energy, or they may use for increasing their potential energy. Like this, whatever the heat energy we are supplying to any of the body, they are utilizing that energy in different ways. If it is utilizing the heat energy more for average kinetic energy, then there is a rise of temperature comes. Okay, so it doesn't mean that every body has to increase their kinetic energy when supplied the heat there. Best example for that is mercury. If you take mercury is having a nature that whatever the heat energy you are giving to the mercury, all the heat energy 90% it is utilizing its heat energy for raising its temperature there, means it is increasing their average kinetic energy. So that's why the mercury raises its temperature very fast. Okay, like this, when compared to one body to another body, say for example silver and iron, if you supply the heat energy same to silver as well as iron, this is silver, actually it raises a temperature very fast, because it is having the nature that it is utilizing all its heat energy for increasing its kinetic energy. So that's why if you supply the same amount of heat for silver as well as for the case of iron, that is silver actually it raises its temperature quickly when compared to the case of iron, some other materials there. Okay, like this, whatever the heat energy we are supplying, all the bodies are not utilizing the heat energy for the same reason. They are maybe utilizing for a different purpose also. Depending on the nature of utilization of energy, the rise in the temperature is different for different substances. Okay, so what is that? The rise in temperature is different for different substances. The rise in temperature is different for different substances, which means it depends on its nature you are taking. Okay, so depending on their nature, okay, depending on their nature, that is. Okay, so all are not raising their temperatures same. Depending on the nature, depending on how they are utilizing the energy, they are changing their temperature, that is. Okay, so means whatever the heat supplied to a substance, it does not depend on the only simply on the mass or not only on the temperature. It also depends how it utilizing the energy, how it is taking the nature of the substance, that is. Now we will see what are the factors that any of the object or any of the substance required while supplying the heat energy. Means the factors affecting heat. Factors affecting heat. When you are taking the factors affecting the heat energy here, the first factor is about mass. Okay, so means about mass. If you are taking any of the two substances, one with more mass, another one with less mass, let us simple case, if you are taking in a container, I am taking first 1 liter of water, and another case I am taking here 2 liters of water, that is 1 liter of water and 2 liters of water if you are taking. Now I am supplying here heat energy for both 1 liter of water and for 2 liters of water. For the same time I am heating that with the same amount of heat energy. Okay, let us suppose here the initial temperature is 10 degrees Celsius, here the initial temperature is also 10 degrees Celsius. Then if you observe that the time taken for this 1 liter water to raise its temperature to 50 degrees Celsius is very less. Very fast it can reach the temperature to 50 degrees Celsius. Whereas if you are taking for the case of this 2 liters of water there, to raise its temperature, actually it takes more time, even though you are taking the same change of temperature from 10 to 50 degrees. Which means that all it depends on the quantity you are taking, because as the temperature raise 10 to 50, 40, 10 to 50, 40, this raise in temperature depends on the kinetic energy of the molecules. If you are taking for the case of 1 liter of water there we are having less number of molecules, whereas in case of 2 liters we are having double the number of molecules are present here. So that's why as each molecule has to increase its kinetic energy, here it takes more amount of heat energy, whereas in this case it is taking less amount of heat energy, that is. Okay, so that's why the amount of heat energy we are supplying is directly proportional to the mass of the substance we are taking. We are considering that when delta T is equal to constant, means for the same rise of temperature. Okay, so for the same rise of temperature, that is. Now the next factor, if you see about the change in temperature, that is. Okay, so when you are supplying the heat energy here Q, now what happens, there is a change in the temperature comes. How much is the change in temperature you want? That much amount of heat energy we have to supply, proportion to that. Means Q is directly proportional to delta T, that is. Then again, if you are taking an example here, taking the same example of taking 1 liter of water, if you are taking in one beaker, and another one also we are taking 1 liter of water again. Both cases, same number of molecules we are taking now. Now what we are doing is, as this is of 10 degrees Celsius initially, and this also at 10 degrees Celsius, I am raising this one to 100 degrees Celsius, whereas I am raising this one only to 50 degrees Celsius. So here the difference in temperature 10 to 100 is 90 degrees Celsius, here 10 to 50, 40 degrees Celsius is the difference here. So which means that here I want more kinetic energy there, because the change in temperature is more, whereas in case of this one 40 degrees Celsius, where the kinetic energy required there is less, even though both are having the same number of molecules, but the molecule is not having the same energy in both the cases. So that's why, as more kinetic energy is required for the first case, so that's why in case of first case we want more rise of temperature. That's why here the amount of heat energy also required there is more. So in both the cases we are taking for the same amount of mass, means mass is constant in this case. Okay, so for the same mass, okay, for the same mass, okay, heat energy is directly proportional to delta T, that is. Then if you combine both the statements M and delta T 1 and 2, now we are getting Q is directly proportional to M and delta T. This is from 1, 2 on combining both the equations. Then we are getting, on taking out that proportion, we are getting a constant here which is K into M into delta T. That K we call that as specific heat capacity, of which earlier only we discussed that we call that as the nature of the substance. Okay, here S is called what? Specific heat capacity. Specific heat capacity, that is. K is equal to S, that is. Then if K is equal to S, finally we got Q is equal to, formula is S into M into delta T. Finally we got a formula for heat energy here, where Q is equal to S into M into delta T, that is, where S is the specific heat capacity and M is the mass we are taking here, and whereas delta T is the change of temperature, that is. Okay, M is equal to mass, delta T is equal to change of temperature, that is. So, and S means, as I said, specific heat capacity, it depends on the nature of the substance. S, it depends on nature of the substance. Okay, so depending on the nature of the substance, S value is different for different substances, that is. Now we got a new formula for heat energy, where Q is equal to, this heat energy means whatever the heat we are supplying, okay, whatever the heat we are supplying to any of the substance, or whatever the heat you are receiving from the substance, that only we are taking that as a delta Q. Okay, how much is the difference in the heat energy? Delta Q is equal to, we got S into M into delta T, that is, where S means, as I said, specific heat capacity, specific heat capacity, and M means mass of the substance, and delta T, which is the change in temperature, change in temperature. Remember, if change in temperature, if you are taking decreasing, means there is a fall in temperature there. Okay, there is a fall in temperature. Then we are supplying the heat to the other body here, means there is a loss of heat. And for suppose if you are getting delta T is increasing, if that is increasing means there is a rise in temperature, it is nothing but gaining the heat, Q gain, that is. Okay, so delta T decreasing means there is a loss of heat, and delta T it is increasing means there is a gain of heat energy is present. for this substance. Okay. Now, in this case, now we got a new physical quantity which is called specific heat capacity, that is. Now, we will see the importance of this specific heat capacity, which depends on the nature of the substance. For different substances, we are having different specific heats are present. Okay, where S means specific heat capacity. Okay. Now, as we know that as Q is equal to Sm delta T, from this we can write S is equal to Q by M delta T, that is, okay, S is equal to delta Q by S into M into delta T, that is. Whereas M is the mass. For suppose if you are taking a unit mass here, M is equal to 1, and at the same time if you are taking the change in temperature is also 1 or 1 degree Celsius. Okay, then our formula becomes S is equal to delta Q, means the specific heat capacity is equal to the amount of heat energy given out or taken, or amount of heat energy required or given out when if you are taking a unit mass of a substance to raise its temperature by 1 degree Celsius or by 1. You can take Kelvin also here. Okay, because change of temperature for degree Celsius and for degree Kelvin both are same, that is. Okay, so see the definition again. Specific heat capacity is the change of heat energy or the amount of heat energy required to raise its temperature by 1 degree by unit mass of a substance. That is the meaning of specific heat capacity, that is. Okay. Now, the best example for this specific heat capacity is in case of water. Okay, specific heat capacity of water we are taking. Specific heat capacity of water is that is equal to 4.2 joule per gram degree Celsius, or you can also write that as specific heat of water is 4.2 joules means 1 calorie, that is. So, 1 calorie per gram degree Celsius also. Okay. So, what do you mean by this specific heat capacity of water? 1 calorie per gram degree Celsius means here water wants, so water requires 1 calorie of heat to raise its temperature by 1 degree Celsius by 1 gram of water. Okay. So, water requires 1 calorie of heat to raise its temperature by 1 degree Celsius by 1 gram of water, that is. Okay. So, here that is the meaning of specific heat capacity. Okay. Because 1 calorie it is about heat and grams that is about mass, and delta C that is about the temperature change there. Okay. So, as S is equal to Q, the specific heat of water is nothing but amount of heat energy required is 1 calorie to raise its temperature by 1 degree Celsius, and the mass you are taking is 1 gram. That is the meaning of specific heat capacity, that is. Okay. Now, when the bodies, two bodies are in contact, here what happens, there is a transfer of heat taking place between one body to another body. Means there may be a change of temperature increasing, there may be a change of temperature here decreasing. If it is increasing, as I said, that is receiving the heat, and whenever if the change in temperature is decreasing, that we can say there is a fall in temperature is present. Okay. Now, based on that, now we are seeing that is about the principle of calorimetry, that is. Okay. So, before going to that principle of calorimetry, now we will see some important about this specific heat capacity, particularly for the case of water. Okay. See, for example, for the case of water, as I said, it is about 1 calorie per gram degree Celsius. If you convert that, actually this is of CGS system. And if you are taking that 1 calorie as 4.2 joules approximate, and 1 gram is equal to, we know that is of 1 by 1000 kgs, and per degree Celsius 1 degree Celsius change is equal to 1 Kelvin, that is kg Kelvin, because 1 degree Celsius change is equal to 1 Kelvin change, that is. Okay. Then if you convert that 1000 coming to numerator, it becomes 1000 into 4.2 joules for kg Kelvin, that is, which is equal to 4200 joule per kg Kelvin. This is the specific heat of water in SA system, this is, and that is for CGS system. But if you observe here, it requires 4200 joules of heat energy by 1 kg of water, which is a huge amount of heat energy is required there. Okay. So means whenever if you want to raise the temperature of water, okay, by just 1 degree Celsius, then amount of heat energy required there is 4200 joules are required here, which is a huge amount of water you are taking. Okay. Huge amount of heat energy we are taking for that 1 kg of water. 1 kg means you already know that that is approximately equal to 1 liter, that is 1 kg of water is equal to 1 liter of water, that is. Okay. So means, for example, if you are raising the temperature by 1 degree Celsius, this 1 liter, I am taking the mass 1 liter, and delta T, this is mass which is of 1 liter, delta T I am taking that about the temperature, let us say 1 degree Celsius. Then what is the amount of heat energy required there? 4200 joules. 4200 joules. Okay. If you are taking 1 kg, then if it is of 1 gram, if you are taking 1 gram, if you are taking for the same 1 degree Celsius, then required amount of heat energy is 1 calorie, that is. Okay, because specific heat of capacity in a CGS is 1 calorie per gram degree Celsius. Then if you are raising this to 1000 grams, which is 1 liter, then raise of temperature is 1 degree Celsius, then amount of heat energy required there is 1000 calories is what required there, which is equal to 4200 joules, 1000 calories. For suppose if I want to boil all the water, means I am raising this temperature of, which is of 1000 grams here, which is of 1 liter of water, to 100 degrees Celsius, then amount of heat energy required there is 1 lakh calories, that is, because 100 into 1000 it becomes 1 lakh calories, that is. So means if you want to boil 1 liter of water, then heat energy required there is 1 lakh calories, which is a huge amount of heat energy, that is. That is the specialty of the water, and that is the nature of the water, which takes more amount of heat energy to raise its temperature. And at the same time, whenever if there is a fall in temperature occurs, it gives out more amount of heat energy. Okay? That is the meaning of specific heat capacity of water, and that is the reason why we are having a very moderate temperature is present on the earth's surface, because of due to the special nature of this water having more specific heat capacity. Like this you can take number of examples there, like in case of watermelon you took. In case of that watermelon, even in our textbooks also we have that watermelon, that outer layer we are having less specific heat capacity, whereas inside the red color pulp we are having more water content is present, so that the specific heat capacity of that part is more. That's why whenever if you take out that watermelon from the refrigerator, actually that outer layer is now coming to the temperature, to the room temperature very quickly, because it has less specific heat capacity. That's why what happened there is the amount of heat energy to be given out is also less. That's why it is giving out very fast. Whereas in case of this red color pulp, if you are taking having more quantity of water is present, then what happens there is the amount of heat energy to given out is more, because for fall in temperature also it has to give out more amount of heat. So that's why it takes more time for this inside part. So that's why if you cut the watermelon there, after some time only the outer surface is coming to room temperature fast, whereas that red color pulp it takes more time for getting to room temperature. Okay, that is the nature of a specific heat capacity of water. Okay, Now we got the formula and we have seen the specific heat capacity of water importance now. Now we will see numerically how to take this amount of heat energy required, which is of as Q is equal to Sm delta T. Then how we can use this formula numerically here? For example, if you are having water, okay, say for example given is like this. If 2 liters of water at 20 degrees Celsius is raised to 50 degrees Celsius, then calculate the amount of heat required. Calculate the amount of heat required. Okay, this is the question. If 2 liters of water at 20 degrees Celsius is raised to 50 degrees Celsius, that is, then calculate the amount of heat required. So here we are having the mass, which is of 2 liters is there, which is of, we have to convert that into, if you are taking the CGS system grams, or if you are taking about the SI system, then we have to convert that into kgs, that is. And we already know that 1 liter of water is equal to 1 kg, that is. Then 1 kg means that is equal to 1000 grams. As we are having 2 liters is there, then it is of like 2 kgs, which means about 2000 grams, that is. If mass is equal to 2000 grams, that is, and we have the change of temperature here, initially that is 20 degrees Celsius, finally that is 50 degrees Celsius. Then final temperature, that is of change of temperature becomes final temperature minus initial, which is 50 degrees minus 20 degrees Celsius, which is of 30 degrees Celsius, that is. Now we got the change of temperature, which is equal to 30 degrees Celsius, that is. Then, and we already know that as S is equal to 1 calorie per gram degree Celsius, then Q is equal to, if you apply Sm delta T, then Q is equal to, S is 1 calorie per gram degree Celsius, M is given 2000 grams, and change of temperature, we are having 50 to 20, which is 20 to 50, increased by 30 degrees Celsius. Then degrees Celsius get cancelled and grams get cancelled. Finally, we got 60,000 calories. Okay, so this is the amount of heat energy required in case of calories, that is, okay, which is of 60,000 calories. Most of the cases will get a doubt that, for suppose if there is a given out heat energy is there, means the same problem if they give, if 2 liters of water at 50 degrees Celsius is decreasing its temperature to 20 degrees Celsius, means from 50 to 20, then again if you have to calculate the amount of heat energy given out, means it doesn't mean that every time we have to take delta T is equal to final temperature minus initial temperature. Change means what we need is only the difference between that. You need not to take following any of the signs here, minus or plus. Always that is taken as positive only. Okay. For example, here this is about raise of temperature we are taking. Now in the same problem, now we are taking, for suppose if there is a fall in temperature is present, how it takes place. If there is a fall in temperature means, let us suppose now I am taking in 1 liter of water, which is of 100 degrees Celsius is there. Now it is falling its temperature, means it is cooled. If 1 liter of water at 100 degrees Celsius is cooled to 0 degrees Celsius. Okay, it is cooled to 0 degrees Celsius. Then calculate the amount of heat given out. Okay, because here now as there is a decrease in temperature, there is a loss of heat energy is present. So means then find the amount of heat energy given out in calories. Okay, then if you are taking the same case, again we are having the mass where M is equal to 1 liter. Okay, and again we are having change of temperature, which is delta T is equal to 100 degrees Celsius minus 0, which is of 100. See, if you see here, I am not taking from final minus initial. What we need is only the change, 100 minus 0. Okay, so it becomes 100. Then again, as S is equal to Q by M, Q is equal to Sm delta T, and we know S is equal to 1 calorie per gram degree Celsius. Then you can write Q is equal to, which is of 1 calorie per gram degree Celsius, mass given there, which is of 1 liter, which is 1000 grams, and change of temperature from 0 to 100, which is 100, that is. Then finally we want 1 lakh calories there, because grams get cancelled and this degree Celsius also get cancelled. So finally we are getting the amount of heat energy required now, which is given out now, is 1 lakh calories, that is. So in both the cases, while raising the temperature for heating the body and for cooling the temperature, giving out for the case there, in both the cases delta T value we are getting positive only. It is not considered as negative. Okay. So other than water, you can take any other example also. For example, in case of if you are using a thermometer there, okay, inside the thermometer mostly we are having mercury is present. Okay. If you are taking for the case of that mercury, actually it's a specific heat. As I said before, the specific heat capacity of mercury is less, because it is having a nature that it is raising its temperature very quickly here. Only less amount of heat is required for raising its temperature, because most of the heat energy it is utilizing for increasing its kinetic energy only. So that's why if you observe here, the specific heat of mercury if you are taking, that is around 0.033 we have, which is of calorie per gram degree Celsius if you are taking. Whereas in case of water, if you take specific heat of water, it is of 1 calorie per gram degree Celsius, that is like this. Okay. Mercury if you are taking 0.033 only, just for 1 gram of mercury to raise its temperature there by 1 degree Celsius. Whereas in case of water, for just for 1 gram, it requires 1 calorie of heat energy here. Now when you are using that thermometer, let us suppose if you are having that body temperature, let it be that is of 100 degrees Celsius there. Okay. And if you are making that temperature reading on the mercury there, of which let us suppose it is taken from 95, that is of, let us suppose if you are taking 0 degrees Celsius on that thermometer scale. Okay. 0 degrees Celsius means I am taking here mercury of which it is of 10 ml is there. So means if 10 ml of mercury at 0 degrees Celsius, okay, 10 ml of mercury at 0 degrees Celsius is raised to a temperature as for normal body temperature on Fahrenheit, that is about 37 degrees Celsius we have around it. Let us suppose if you are having more, let it be that is of 40 degrees Celsius we have. Okay, is raised to a temperature of 40 degrees Celsius, then the amount of heat energy transferred to the mercury is, means our body is losing the heat energy and we are supplying the heat energy to the mercury here. For suppose if our body temperature is around 40 degrees Celsius if you are taking, then in that case if you use the formula Q is equal to Sm delta T again, then S value it is given there which is of 0.033 and its mass given which is of 10 ml, that is 10 ml means 10 grams, that is, okay, 10 ml means 10 grams, that is, okay, into change of temperature from 0 to 40 degrees Celsius, which is of 40 minus 0, 40, that is. So 0.033 which is 33 by 1000 into 10 into 40 minus 0 which is 40. Both the zeros get cancelled and finally we got 33 into 4, 132 by 10. which is of only 13.2 calories only it is taking there. Okay, only 13.2 calories we are getting. So means if you are using that thermometer scale there, okay, of which we are having only 10 ml of mercury is present inside that, actually we are having very less in that. Okay, so if you are taking 10 ml of mercury there at 0 degrees Celsius, if you make that, and if you are raising the temperature to 40 degrees Celsius up to our body temperature or the room temperature, then we are getting the amount of heat energy transferred to the mercury is only 13.2 calories only we are getting. Okay, have understood now? So like this we can solve for the specific heat capacity in case of water you can take, or in case of mercury you can take. Okay, this is about supplying the heat. And in the same way, if you are supplying the heat energy to some substance, means there is a rise in temperature. No? So let us suppose if you are taking for the case of rise of temperature there, means here I am supplying the heat energy to water, and now there is a rise in temperature takes place. Okay? Now I am say for example, if you are supplying 1000 calories of heat, means if 100 grams of water at 20 degrees Celsius is heated by supplying 2000 calories of heat, then calculate the rise in temperature. Okay, calculate the rise in temperature, that is. And we know that as M is given as, which is of 100 grams, and change of temperature we don't know, and given that this time heat energy is given, which is Q is equal to 2000 calories is supplied there. Then again if you know that as Q is equal to Sm delta T, whereas S is equal to 1 calorie per gram degree Celsius, then as Q is equal to Sm delta T, S is 1 calorie per gram degree Celsius, mass it is of 100 grams, and change of temperature we are taking, of which we don't know how much is the rise in temperature. Let it be that is delta T only. Okay, and supplied heat energy it is of 2000 calories is there. So that calories, and here the grams get cancelled and both the zeros get cancelled here. Then delta T becomes 20 degrees Celsius, that is. So delta T is equal to 20 degrees Celsius means here we are taking heating. Heating means there is a rise in the temperature there. As there is a rise in temperature takes place, here the final temperature becomes, initially that is 20 degrees Celsius, now raised by how much is plus 20 degrees Celsius. Then how much it becomes is in total 40 degrees Celsius. So if you are supplying a heat of 2000 calories to 100 grams of water, if it is at 20 degrees Celsius, finally we are getting to a temperature of how much, that is 40 degrees Celsius. Okay, I have understood now how to find if the heat energy is supplied, how to find the rise in temperature, and in the same way if you want to raise the temperature, how much is the heat energy required, like this. Okay.